Students, it's good to top in exams, but be cautious not to fail in life, otherwise, you will be an everlasting loser. Stop mugging up the subject. Avoid any sort of rote learning, avoid any sort of cramming, and start experiencing it. Enjoy your studies, try to understand the concepts because you are a human being and not a robot. Mark my words, students.
Jai Hind students, welcome to my YouTube channel. In this lecture, I will mathematically verify the lens equation for both convex lens as well as for concave lens. So let's start with the convex lens. And here we have got two cases. We are aware when the object is placed beyond the focus in front of a convex lens, then the nature of the image obtained is always real, right? So we will prove lens formula when the image is real. And in the second scenario, when the object is placed between the optical center and the focus, then the nature of the image obtained is virtual, right? So for that case also, we will prove lens formula. In both the cases, the formula will remain valid. So basically a lens formula, which is the relationship between U, V and F, it is valid for every type of lens, be it converging lens or diverging lens. It is valid for any nature of the image, whether the image nature is real or virtual. So let us verify this fact. So let's consider case 1. Case 1 is when the nature of the image obtained is real, right? So let's try to prove it. So let's draw the diagram. So this is a convex lens. This is the optical center, students. And suppose this is the principal axis. Now you need to locate these reference points F to F. As I have told you numerous times, they are to be equidistant. These are all equidistant. We are dealing with biconvex lens. So please ensure that these distances are equal, right? So image obtained should be real one. So the object is to be placed beyond F. Beyond F you can place anywhere. The object can be placed anywhere beyond F. In such a case, the image obtained would be real. So this is the reference line from where the deviation of the path will be considered. So suppose object is placed over here, AB. We have already done this case in the ray diagram, right? So we are aware of the rules. A ray which is parallel to the principal axis, after suffering refraction, in the case of convex lens, it will tend to pass through the focus like this. It will tend to pass through the focus. Right? Second, student, this is the optical center. It is a point within the lens from where the light, when passes through this particular point, remain undeviated. So that's the second rule. So light from the object, when passing through the optical center, it will remain undeviated. So this is where the intersection of the two refracted rays will be obtained. Okay, this is the point. And I told you, whenever the two dark lines intersect, it means that the nature of the image must be real. Two dotted lines, that is virtual. One dotted line, that will be again virtual. So here we will drop a perpendicular. So this is the inverted enlarged image obtained, A dash, B dash. So we are already aware of this situation, isn't it? Whenever the object is placed between F and 2F, then its real, inverted, enlarged image is obtained beyond 2F. Clear? We have already done it. So we have already studied the nature of the image form. Right? So let's name it. This is AOB, this one is A dash, O, B dash, and let us consider this to be M. Let us consider this point to be M. Now look, these are the two parallel lines, so obviously OM, it should be equal to AB. These two distances are equal, these two being parallel lines, right? Now what to do is, we need to consider two pair of triangles, right? Students, you must remember the manner in which we have derived mirror form. In this case also, we need to proceed with the similar fashion, right? So what to do is, let's consider triangle AOB, let's consider triangle AOB and triangle A dash OB dash, and let's consider triangle A dash OB dash. Now look students, this angle is equal to this angle. These are vertically opposite angles, isn't it? This is 90 degree, this is also 90 degree. So by AA corollary, these two triangles are similar. Look, AOB, this triangle, is similar to this triangle, A dash OB dash. So these two triangles being similar, their corresponding sides must be proportional. So these two triangles are similar. Therefore, their corresponding sides are proportional. Corresponding sides are proportional. That is, consider A dash B dash. A dash B dash. Students, what will be its corresponding side of the other similar triangle? That is AB. So let's consider base of this big triangle, OB dash. What's the base of this smaller triangle? It is OB. You need not to consider this hypotenuse, it's of no use. So put this as equation number 1. I hope it's pretty clear. These two triangles being similar, their corresponding sides are proportional. So that is how we have managed to obtain this particular equation, right? We need to choose second pair of triangles. So what to do is, we consider these two triangles as well. Consider these two triangles. This triangle and this triangle. These two triangles are also similar. Now look, this is 90 degree, this is also 90 degree. And this angle is equal to this angle, being vertically opposite angles, isn't it? So these two triangles, MFO and A dash FB dash, are also similar. That is, triangle MFO is similar to triangle A dash FB dash. Therefore, students, again the corresponding sides must be proportional and ensure the left hand side of both the equations must be same. So these two triangles being similar, their corresponding sides are proportional. So let's take A dash B dash. A dash B dash. The corresponding side of A dash B dash would be OM. And students, OM is equal to AB. OM is equal to AB. So left hand side of these two equations becomes equal, right? And it's equal to, let's consider base. Base of the bigger triangle. It is FB dash. What about base of the smaller triangle? This one. That is OF. So please ensure that after obtaining these two equations, the left hand side of these two equations must be same, so that we can equate the right hand side of these two equations, right? So again I repeat, consider two pair of triangles, they must be similar, prove that they are similar, and then the corresponding sides are proportional. So you will be able to obtain these two equations, right? And write the equation in such a manner that the left hand side are equal, so that we can equate the right hand side of these three equations. So from 1 and 2, what we get is, from 1 and 2, we get OB dash divided by OB is equal to FB dash divided by OF, right? Now look students, as per the new Cartesian Sine Convention, we all are aware that the distances are to be measured from the optical center. So no need to change these terms because they are already having O as the initial letter. FB dash needs to be changed. So FB dash may be written as OB dash minus OF, isn't it? FB dash may be written as OB dash minus OF. So what to do is, OB dash divided by OB is equal to FB dash. It is OB dash minus OF divided by OF. Now all the terms are initializing with letter O. Right? Now we can make use of Sine Convention. So let's make use of Sine Convention. Using Sine Convention. And we are all aware, all the distances measured along the direction of the incident ray from the optical center are to be taken as positive. Else, the distances measured from the optical center against the direction of the incident ray are to be taken as negative. So let's make use of the Sine Convention. OB, it's measured against the direction of the incident ray. This is the incident ray. This is the incident ray from left to right. So OB is measured from right to left. So obviously it is to be taken as negative. OB, it's the object distance. OB dash. OB dash is measured along the direction of the incident ray, and whenever image is real in case of lens, it would be positive. What about OF? Focal length of convex lens, OF, that's positive. Plus F. This is the real focus. Real means positive, right? OF, it's measured along the direction of the incident ray, that is from left to right. Now students, let's substitute these values. So what we get is V divided by minus Q is equal to OB dash, that is V minus F divided by F. You can cross multiply it. Let's check it out. So what do you get is VF is equal to minus UV plus UF. So still further, what we'll do is let's rearrange the terms. So we get UV is equal to UF minus VF. Simply rearrange the terms, right? UV when taken on left hand side, its sign will get changed and replace UV with VF. So we'll get this. Now students, in the last step, divide throughout by UVF. Dividing throughout by UVF. What we get is UV divided by UVF is equal to UF divided by UVF minus VF divided by UVF. So what do we get? 1 by F is equal to 1 by V minus 1 by U. So student, this is the relationship between object distance U, the image distance V, and the focal length F. And this relationship is known as the lens formula or the lens equation, right? So this is applicable in case of lens. Students, you must remember, in the case of mirrors, the mirror formula is 1 by V plus 1 by U equals to 1 by F. The lens formula is 1 by V minus 1 by U is equal to 1 by F. So this is the mathematical verification of lens equation. Simply by considering two pairs of triangles and equating their corresponding sides being proportional and equating those two equations and using Sine Convention, we can easily find this particular result, right? Now, we can also find out the expression for the linear magnification. So for that, what to do is, let's consider, students, let's consider equation 1. Let us consider equation 1, this one. Now here, let's make use of the Sine Convention directly. So let's see what we get. A dash, B dash. Now as I told you, the distance is measured perpendicular to the principal axis and in the downward direction. That is to be taken as negative. I told you, the size of the image is considered to be H2. The size of the object is considered to be H1. So there the image is inverted, measured downward. So it is to be taken as negative. So it is minus H2. I am making use of Sine Convention, right? What about AB? It's measured perpendicular to the axis and in the upward direction. So it is plus H1. Make use of Sine Convention. What about OB dash? OB dash, it's plus B. OB dash, it's plus B. And what about OB? OB, incident ray is along this direction and OB is measured against the direction of the incident ray. So it needs to be assigned negative sign. So minus minus, it will get cancelled out. So we get H2 by H1 is equal to V by U. And students, the ratio of size of the image to the size of the object is known as linear magnification. So this is the formula for the linear magnification in terms of object distance and the image distance in case of lenses. Here I must mention that in the case of mirror, linear magnification is minus V by U, while in case of lens it is plus V by U. So this is how we are able to easily mathematically verify the lens formula as well as the formula for the linear magnification. Right, students? So case 1 is over. Now as we are aware, in a convex lens, nature of the image may be either real or it may be virtual. In case the object is placed beyond F, the nature of the image is always real. Now in case, this is an exceptional case, in case the object is placed between optical center and the focus, then the image is formed on the same side as that of the object. And in that case, the nature of the image is virtual. So we'll prove the lens formula for the virtual image. So let's consider case number 2. Let's try case number 2. Here ensure to place the object between the optical center and the focus. Optical center and the focus. So let's start with case 2. So when image is virtual. And this is case 2. Let's draw the ray diagram first. So this is the ray diagram. This is the lens, convex lens, this is the optical center. This is the principal axis. This is suppose the focus. This is the reference line from where the deviation of light is to be considered. Object, remember, it is to be placed between optical center and the focus. And this is the real focus of the convex lens. So what's the first rule? Ray parallel to the principal axis. After refraction, it will tend to pass through the focus. What's the second rule? The ray passing through the optical center, it will remain undeviated. So obviously students, these two refracted rays will never intersect over here. The gap between them keeps on increasing. So what we'll do is, we'll produce it in the backward direction. That is, we'll try to draw virtual lines, dotted lines. So let's see. So image would be formed on the same side as that of the object. Image will be formed on the same side as that of the object. So this is the case where the nature of the image obtained is virtual, like this. Here the image is formed. So as I told you earlier, the intersection of two dotted lines, that will represent virtual image. This is A dash, this is B dash. So students, what's the nature of the image? Virtual. It is erect, formed on the same side as that of the object, and it is magnified, right? So the nature of the image is virtual. Let's verify lens formula for this case as well, right? So what to do is, consider this to be M, consider this point to be M. Now obviously AB is equal to MO, these two are equal, thus being parallel to the principal axis, right? We need to consider two pair of triangles. So what we'll do is, let's consider triangle A dash OB dash and triangle AOB. Students, consider these two triangles, A dash OB dash and triangle AOB. This angle is common. This is the common angle. And this is 90 and this is 90. So these two triangles by AA corollary are similar. Therefore, their corresponding sides must be proportional. That is why A dash B dash divided by corresponding side of A dash B dash is AB, and it is equal to consider base OB dash divided by OB. Put this as equation number 1. Right? Wherever applicable, do start writing the distance from letter O, optical center. Okay, we need to consider the other pair of triangles as well, right? For that, what we'll do is, consider this triangle, the bigger one. That is, consider triangle A dash F B dash. Consider triangle A dash F B dash. This one, students. A dash F B dash. And consider this triangle, this one. MFO. MFO. Triangle MFO. Again, I am repeating. Students, consider triangle A dash F B dash and triangle MFO. This angle is common to both the triangles, and this is 90 degree, this is also 90 degree. So these two triangles by A corollary are similar. Therefore, their corresponding sides again must be proportional. So while writing the equation, please ensure the left hand side of both the equations must be same. So A dash B dash. What's the corresponding side of A dash B dash? It's MO. And students, MO is equal to AB. So that the left hand side of these two equations becomes equal. And it is equal to, let's consider the base. What's the base of the bigger triangle? B dash F. Divided by, what's the base of the smaller triangle? That is OF. Okay, we have obtained these two equations. Now students, what to do? We need to equate these two because left hand side of these two equations are equal. Therefore, from 1 and 2 we get, from 1 and 2 we get OB dash divided by OB is equal to B dash F divided by OF. Now look, as per the Sine Convention, all the distances are to be measured from the optical center. The initial alphabet should be capital letter O. So B dash F needs to be changed. This is B dash F. B dash F may be written as OB dash plus OF. Again I repeat, B dash F may be written as OB dash plus OF. So what we get is OB dash divided by OB is equal to OB dash plus OF. Here I have written B dash F as OB dash plus OF. Right? Now all the distances are measured from optical center. Now we can make use of Sine Convention. So using Sine Convention, what we get is, let's make use of Sine Convention. Here again the same rules. The distances measured along the direction of the incident ray is to be taken as positive. This is the direction of the incident ray. That is from left to right. This is the object, this is the incident ray, right? So all the distance measured from O along the direction of the incident ray will be taken as positive. So OF is positive, obviously. Focal length of a convex lens is real, so it's positive. What about OB? It's minus U. What about OB dash? It's minus V. Virtual image, it will have negative sign, right, in case of lenses. So let's substitute these values over here. So OB dash is minus V, OB is minus U is equal to OB dash again minus V plus F divided by F. Minus minus get cancelled, so we'll be left with this. Let's cross multiply. Therefore, what we get is VF is equal to minus UV plus UF. So it can be also written as UV is equal to UF minus VF. Correct, students? So in the last step, you are aware, we need to divide throughout by UVF. So dividing throughout by UVF, we get dividing throughout by UVF. We will get the desired result. So what we get is UV divided by UVF. So 1 by F would be left. Over here, UF divided by UVF. So 1 by V would be left. And here, 1 by U is left. So this is, student, the lens formula. And as I have stated, this formula is valid whether the image is real or it is virtual. It is immaterial, it is of no consequence whether the image is real or virtual. In both the scenario, this formula between U, V and F, this relationship between object distance, image distance and focal length will remain applicable, right? So that's lens formula for you in case of virtual image. Now let's try to verify the expression for the linear magnification as well. So consider first equation. Consider first equation. So consider equation 1. What you get is A dash B dash divided by AB. This one, A dash B dash divided by AB is equal to OB dash divided by OB. OB dash divided by OB. Let's make use of the Sine Convention. As you are aware, height of the object H1, height or size of the image, that is H2. So both are erect. Both are measured perpendicular to the principal axis and in the upward direction. So as per the convention, both are to be assigned positive sign. So A dash B dash is plus H2, AB is plus H1, OB dash, make use of the Sine Convention, OB dash is minus B, OB is minus C. So linear magnification, as you are aware, students, it is defined as the ratio of the size of the image to the size of the object, which would be V by U. So look, the same formula has been obtained both for real image as well as for virtual image. So students, this is the mathematical verification, right, for obtaining the lens formula as well as the expression for linear magnification in terms of U and V. So convex lens, both the cases are covered. we'll try to derive the lens formula for concave lens. And students, as you are aware, in the case of concave lens, the image obtained is always on the same side as that of the object. What I mean to say is that image is always virtual, erect, and it is diminished, right? So let's start with the mathematical derivation of lens formula. So suppose this is the concave mirror, this is the concave lens actually, this is the concave lens which is thin at the center and thick at the edges. This is the optical center and this is the reference line. This is the reference line. And suppose this is the principal axis, right? Let us consider this to be focus. This is the virtual focus of this concave lens. An object may be placed anywhere. Wherever the object may be placed in front of a concave lens, the nature of the image obtained is always virtual, erect and diminished, formed on the same side as that of the object. Suppose the object is placed over here. Suppose this is the object. This is an erect object placed over here. AB. Its height is h1. Size of the object is h1. Look, this is it. First rule. As for the first rule, the ray which is parallel to the principal axis, after refraction, it will appear as if it is coming from the focus. So it will be like this. So if you produce it in the backward direction, it will appear as if it is coming from the focus. Right? So that is the very reason why concave lens is also known as a diverging lens. And students, what's the second rule? Second rule is incident ray while passing through the optical center of the lens will remain undeviated. It won't get any sort of bending, right? So its path will remain undeviated. So it's like this. Its path will remain undeviated. So this is the intersection of dotted line and dark line. So here, if you drop a perpendicular, this virtual erect diminished image will be obtained. This is A dash and this is B dash. Clear, students? We have already done this particular topic of the image formation in case of concave lens. This again, I am repeating this particular topic. Suppose this point is N. Now this ray being parallel to the principal axis, these are the perpendicular distances, so it will be same. And we'll proceed in a similar manner. Like we need to consider two pair of triangles, we need to prove that they are similar, the corresponding sides are proportional, right? So let's proceed with a similar manner. So let's consider triangle AOB, AOB. I'm considering this triangle, and consider triangle A dash OB dash. I'm considering triangle AOB and triangle A dash OB dash, the smaller one. Look, students, this will be the common angle. This is 90 degree, this is also 90 degree. So these two triangles are definitely similar. Therefore, their corresponding sides must be proportional. So let's consider A dash B dash. The corresponding side of A dash B dash is AB. The corresponding side of OB dash of the smaller triangle is OB in the bigger one. So you can put it as equation number 1. So that's the first pair of triangle, and they are similar, therefore their corresponding sides are proportional. We have to find the other pair of triangles as well, right? So what to do is, we can consider these two triangles. Look, MFO, this is one of the triangle, and A dash FB dash. So I am considering these two triangles, MFO, this triangle, and A dash FB dash. So again, this would be the common angle, and this is 90 degree, and this is also 90 degree. Therefore, triangle A dash FB dash must be similar to triangle MFO. A dash FB dash must be similar to triangle MFO. Right? So the corresponding sides are proportional. Again, students, please ensure that the left hand side should be same. So A dash B dash, A dash B dash, its corresponding side would be MO. And students, MO, it's equal to AB. So that the left hand side of these two equations becomes equal. It is equal to, now consider base of the smaller triangle. So base is B dash F. divided by, of this triangle, the base is OF. Right? So, from equation 1 and 2, it's pretty clear that the left hand side are equal, therefore we can equate the right hand side. So therefore, from 1 and 2, we get OB dash divided by OB is equal to B dash F divided by OF. Now as we are all aware, all the distances are to be measured from the optical center. So initial letter, initial alphabet should be O. So no problem with these three terms. But B dash F needs to be changed. This is B dash F. B dash F. This can be written as OF minus OB dash. B dash F may be written as OF minus OB dash. So what we get is OB dash divided by OB is equal to B dash F is OF minus OB dash. Right? Now let's make use of Sine Convention. So what we get is using Sine Convention. Okay. Let's consider OB. Incident ray is along this direction. This is the direction of the incident ray. So all the distances from the optical center measured along the direction of the incident ray are to be assigned positive side, and against the direction of the incident ray are to be assigned negative side. So its focus is virtual. So OB, OB dash, OF all are measured in a direction opposite to that of the incident ray. Therefore all are negative. So OB is equal to minus U, OB dash is equal to minus B, and OF is equal to minus F. The focus of a concave lens is negative. So whenever it is placed in some river medium, so its focal length is always negative, right? So it's virtual. So let's substitute these values over here. What do you get? OB dash, that is minus U divided by OB minus U is equal to OF minus F minus OB dash minus B divided by minus F. So let's solve it. V by U, it will be equal to minus F plus V divided by minus F. On cross multiplying, we get minus VF is equal to minus UF plus UV, or UV is equal to UF minus VF. Rearranging the terms, we can write it like this. And students, you remember in the last step, we divide throughout by UVF. So what we do is dividing throughout by UVF. Dividing throughout by UVF. So we get 1 by F is equal to 1 by B minus 1 by B. This is lens formula for you. So the same formula is valid for concave lens as well. Right? This is known as lens equation of lens formula. It is a mathematical relationship between the object distance, image distance, and the focal length, all measured from the optical center of the lens. So students, we can make use of this equation 1 so as to obtain the expression for the linear magnification as well. So let's do that. So directly we can make use of Sine Convention in equation 1. So what we get is okay, A dash B dash. This is the image, this is the size of the image H2. Now look, it is erect, the object obviously is erect, so both are measured perpendicular to the principal axis and in the upward direction. So both are to be assigned positive side. So A dash B dash, it will be equal to plus H2. AB being erect, it is plus H1. OB dash, it is minus B. OB, it is minus B. So what do you get? H2 by H1 is equal to V by U. And students, you are aware, the ratio of the size of the image to the size of the object is known as linear magnification. So this is the expression for the linear magnification. Clear? So in case of concave lens, we have both mathematically derived the lens formula as well as the expression for the linear magnification. So before we start with the numericals based on lens equation and linear magnification, let's recapitulate some important facts between mirror and lenses. Students, there shouldn't be any sort of confusion between mirrors and lenses. Every concept should be crystal clear. So let us revise those topics so that you don't get confused. So what we'll do is, we'll prepare 2 columns and then we'll discuss the related concepts, right? So suppose this is in case of mirrors. Let's dedicate the first column to mirrors. And here for lenses. Okay. First and foremost point. In mirrors, student, when light is incident, then what happens? It bounces back into the same medium. So, reflection. So, in mirrors, reflection takes place. And not refraction, right? Obviously, when light gets incident on a mirror, partly it will get reflected, partly it will get absorbed, right? But refraction will not take place. So in mirrors, reflection does take place. While in the case of lenses, that is light traveling from rarer to denser, that is from air to lens which is made up of glass, what happens? The path of the light gets bent. And as you are aware, students, this phenomenon of bending of light or the phenomenon of change in the velocity of light is known as refraction. So in the case of lenses, refraction takes place. Refraction takes place. Okay. Now second, in case of mirrors, friends, just remember, if the image is formed on the same side as that of the object, then a screen can be placed at that position and the image can be obtained on the screen. So in case of mirrors, real images are formed on the same side as that of the object. So real images are formed on the same side as that of the object. Right? Like this is a mirror, whether you consider concave mirror or convex mirror doesn't matter. And this is F, this is C. So if an object is kept over here, its image will be formed somewhere over here. So if you place a screen, then its image can be obtained. So what I mean to say is that in the case of mirrors, the image, real image is formed on the same side as that of the object. This is the object and this is the image. Is it clear? While in the case of lens, this is a lens. Suppose here object is placed. So in case image is formed over here, then a screen can be placed over here and this image can be obtained on the screen. So I hope you have got the basic difference. In the case of lenses, real image is obtained on the opposite side as that of the object. Opposite side of the object. Right? So this is the basic difference. There shouldn't be any sort of confusion. Students, in case of mirrors, the real images are always formed on the same side as that of the object. While in case of lenses, the real images are to be obtained on the other side as that of the object. On the other side as that of the object. Right? Okay. Let's consider next case. What about virtual images? In this case, virtual images are formed like this. This is O, this is F. If an object is placed over here, its virtual object is formed, virtual image is formed like this. This is the object and this is the image. So basically in mirrors, virtual images are formed behind the mirror. While in the case of lenses, virtual images are formed on the same side as that of the object. So in mirrors, virtual image is formed behind the mirror. While on the other hand, in the case of lenses, like there is a convex lens and there is the optical center, there is the focus. Suppose an object is kept over here. So here its virtual image is formed. This is the object and this is the image. So here virtual image is obtained on the same side as that of the object. So over here virtual image is formed on the same side as that of the object, on the same side as that of the object, and therefore it can't be obtained on the screen. So students, these are some very important facts. There are some other differences as well. Let's discuss those differences also. Now, the relationship in U, V and F in case of mirrors, that is known as mirror formula. And mirror formula is, you are aware, it is 1 by V plus 1 by U is equal to 1 by F, right? So fourth point. What about mirror formula? Mirror formula is 1 by V plus 1 by U is equal to 1 by F. This is mirror formula. And just now we have discussed lens formula. Lens formula also connects, or rather it is a relationship in U, V and F. But for lens, the formula is 1 by V minus 1 by U is equal to 1 by F. That's lens formula. Right? Then, linear magnification. In both cases, it is defined as the ratio of the size of the image to the size of the object. In both the cases, linear magnification is defined as the ratio of the size of the image to the size of the object. But in case of mirrors, in terms of image and object distance, it is minus V by U. While in case of lens, it is plus V by U. Right? There shouldn't be any confusion, students, right? Do study these topics very carefully. Okay, next one. In case of mirrors, there are two types of mirrors, concave and convex mirror. Concave mirror is known as a converging mirror. Concave mirror is known as a converging mirror. While convex mirror, it is known as a diverging mirror. It is known as a diverging mirror. Right? While in the case of lenses, we have discussed concave lens. It is known as a diverging lens. It is known as a diverging lens. While on the other hand, convex lens, it is known as the converging lens. So these are essentially some very important comparative study between mirrors and lenses. So students, I must tell you, there shouldn't be any sort of confusion. In case of a numerical, just try to understand the numerical, whether it is the case of mirror or lens, then apply the appropriate Sine Convention, and then using appropriate mathematical formulae, we can solve it. So in the next lecture, what we will do is, we will discuss some numericals based on lens formula and linear magnification. And we need to also discuss regarding the power of a lens. But we will discuss those topics in the next episode. Till then, do take very good care of yourself and study well.